Hi everyone, welcome to Anesthesia Coffee Break. And again, we're talking about respiratory physiology with Archit, who's, you've just got onto the Crit Care training program and you're going to be studying for your primary exam properly very soon, I imagine. So yeah, good luck to everyone.
Very soon, very soon. It comes around quickly for everyone.
So what are we talking about today, Archit?
I think today we're going to be talking about like a crucial topic of dead space. We'll start off with dead space and then sort of go from there. And it's one of those topics that's, it definitely needs to be talked about.
Beautiful. There's a few kind of really tricky concepts with this, but we'll try to keep it as simple as possible. So describe dead space. The syllabus point itself is describe dead space, its measurement, and apply the Bohr equation. So let's get started. What is dead space?
Yeah, dead space is an area of lung where there's ventilation but no perfusion. And I like to think about it as dead or wasted ventilation. So AKA dead space.
Beautiful. And maybe instead of using the word area, just if you were to say volume, the volume of lung. But yeah, when you meant area, it was like, oh, that part
Yeah.
of the lung, which
Yeah.
makes sense. Technically volume. So that's good. Let's go through. There's a whole bunch of definitions that are probably useful in this context. What is minute ventilation?
Yeah, so minute ventilation is the volume of gas entering the lungs over a minute. So that's tidal volumes times ref rate.
Fantastic. Imagine when you set your ventilator, there's 500 mils tidal volume and a respirator of 12. That's roughly 6 liters per minute in some average individual. So the other way they've described dead space, if you want to just have a sharp definition, the volume in the respiratory system that does not participate in gas exchange. So just pause and imagine what that is. You've got air going in and the oxygen is not going into your capillaries. There's no connection there. There's no blood flowing in whatever section that is. So there's a number of components. Let's actually just start with physiological dead space. What's that?
Yeah, physiological dead space is the part of the tidal volume that does not contribute to gas exchange. So physiological dead space equals alveolar dead space plus anatomical dead space.
And so if you think about it, physiological dead space often is just dead space. But we're going to be specific because there's a few different types of dead space that could occur, especially when you have an endotracheal tube in. So what is anatomical dead space?
Yeah, again, it's volume of conducting airways in which gas exchange does not occur. So we've previously spoken about this, and gas exchange doesn't occur until about the respiratory zone. So anything prior to this is technically anatomical dead space.
Right. And that's about 150 mils. So if you think of when you're ventilating an adult, if your tidal volumes are 150 mils, potentially, assuming that flow is very uniform, which it isn't, 150 mils is kind of inadequate in many circumstances. That's not always the case. You can actually oxygenate someone fine with 150 minute tidal volume, but you've got other factors such as the gas flow and diffusion that also play a part in this. So let's just skip that for now. So anatomical dead space is that. How about alveolar dead space?
Alveolar dead space is the proportion of the tidal volume beyond the anatomical dead space that does not take part in gas exchange. So anything after our anatomical dead space that still doesn't take place in gas exchange, that's your alveolar dead space.
Yeah, exactly. So this is generally going to be because there's something wrong with the capillary alveolar interface. So for example, if you have really bad hypotension, suddenly you might have closure of your capillaries, your pulmonary capillaries, which means that there's no gas exchange happening, or maybe you've got this massive pulmonary embolism blocking a part of the capillary. Therefore, again, blood's not flowing past. Therefore, there's no gas exchange. Often we'll go into this in another section, but that's called West Zone 1 in some instances. Okay, what is apparatus dead space?
Yeah, apparatus dead space, I guess, is very relevant to us as anaesthetists, given that we introduce apparatuses into our breathing circuits. So it's the dead space introduced in the breathing circuits used for mechanical ventilation, where the volume distal to that Y piece that we attach on, which doesn't take part in the gas exchange.
And I find this extremely important when you're ventilating small children, because suddenly the total amount of your tidal volume and the dead space it's such a massive fraction of what's going on. So sometimes to overcome this, practically speaking, you got to, first of all, you got to make sure that you have adequate volumes. For kids, especially if they're spont venting, they might not be spont venting adequately, but also having enough gas flow. And back in the day, I mean, still now, we use TP circuits. Often these TP circuits, we have to use high flows for them so that it becomes a lot of this problem. But with circle circuits, sometimes you'll be running low gas flows, and that could be a problem. And it gets really complicated, especially with long connections, long circuits, and things like that. But essentially, you'll have lots of different circuits, but the answer to this question is the volume distal to the Y piece. So the volume distal to the Y piece. How do you measure total ventilation?
So total ventilation is measured via when a subject actually breathes through a valve box, and then it separates out from the inspired from the expired gases, and then everything is collected out together in a bag, and then it's measured as a
Yeah,
total
so
ventilation.
in this exam, we would have mentioned they'd love to ask you how would you measure something, and such a basic question like that could really throw people because, like, well, how on earth do we actually find out the volume expired gases? Unless we're actually just calculating each tidal volume, measuring it. Yeah, there's actually this valve box and a bag that collects things through a very simple mechanism like that. Let's go through alveolar ventilation. How do you calculate that?
So you basically calculate your anatomical dead space and then subtract that from your total ventilation.
Great. So now we've got all the method of doing this. We can calculate anatomical dead space, which we're going to go into in a second. That's through a specific method, and take that away from total ventilation, which we've calculated by that valve box mechanism. And there we have your alveolar ventilation. Maybe useful in very specific circumstances with respiratory measurement. Let's go on to how you measure these things, the second part of this syllabus point. So how do you measure anatomical dead space?
Yeah, and jump in here at any moment, Lahiru,
Yeah,
because
that's right.
this is one of those things where we will need your help. Anatomical dead space is measured with the Fowler's method of measuring this thing, which we've actually almost touched on previously in one of our other episodes when we talked about the closing capacity. So it's a very similar measurement to that in the nitrogen dilution. So firstly, the subject takes a big breath in and of 100% oxygen. This oxygen then sort of displaces all the other gases from the respiratory tract so that at the end of the inspiration, you've got anatomical dead space is completely filled with just pure oxygen. So when the subject exhales, and there are three phases that are observed in the graph. The initial sort of gas that comes in and the sensor measures complete pure oxygen. So there's no nitrogen. So I should mention that the sensor actually measures nitrogen in this case.
Yep.
So at the start in phase one, there's absolutely no nitrogen because if you think about it, you've breathed in all that oxygen, and then when it comes out, you've got that first part of your dead space that's just oxygen that's coming out there. I'll talk about the second phase in a second, but the third phase is where there's mainly sort of the contents of gas exchange alveoli and will be relatively rich in nitrogen, and that nitrogen will be stable. So this is a plateau of the Fowler's phase in phase three. In phase two, in the middle, there's a phase where it's exhaled nitrogen concentration rises really quickly, like exponentially quickly. And this is because of the fast time constant alveoli mixing with the gas and from the more distal airways. So here you've got some diagrams up there.
Yeah, so again, if people are watching on YouTube, just go to the primary exam playlist or the anesthesia coffee break playlist, and you'll be able to see the diagrams. Again, they're in West's respiratory physiology. So that's a reasonable explanation. Now, I think one point that was made was it completely. So when you take that single 100% oxygen breath, that it completely displaces all the other gas, and that's not true because as you can see, you're measuring nitrogen. You're simply taking one volume breath of oxygen, 100%, because that will fill up your anatomical dead space, but it doesn't displace all the nitrogen. So you can see that the end alveolar, part of your breath will still, or the end tidal part of your breath, which represents alveolar gas, still has nitrogen. So that's the whole purpose of that you're not completely nitrogenating this. They often ask how you would how you would construct this. So you mentioned those correct things. You have a nitrogen analyzer, so that's important. You've got oxygen, so that the subject can breathe in, and you can measure, and you have to measure flow or measure volume. So often they talk about having a pneumotachograph or some flow meter, which you can measure flow and then integrate with respect to time to get graph B. So that's one of those important-ish points where you're measuring nitrogen concentration per time. So that's not the values you want. You need to integrate the flow with respect to time. Again, thinking back to high school maths, where liters per second integrated to time in seconds equals your liters. So hopefully that makes sense. The important part of this, exactly as you said, imagine that one breath is oxygen. As you breathe out, your anatomical dead space has oxygen, so you record no nitrogen. Then as you get this transition from alveolar gas and transition from anatomical dead space to alveolar gas, you get this rapid upstroke. That's your sinusoidal curve looking thing. And then once it's total alveolar gas, that's when you get the plateau where it's just high nitrogen concentrations. Now, they talk about this point. So if you look at the point at which you judge is anatomical dead space is a point where if you were to bisect the sinusoidal S part of that curve with area A equaling B, again, best to just look on the graph, that it's a relatively arbitrary point. It's a good estimate that roughly the volume from up to that point, that is your anatomical dead space. And so starting from 0, you see 0.2 liters there. It's just before that. That's 150 mils, and that's where you get this value from. A few important things there. How you measure it, it's just one breath. You get this rapid change in your nitrogen concentration where the area is half. You bisect that line, and then the intersecting point is at a point of volume on the x-axis. That's your anatomical dead space. Hopefully people can, really get an understanding and, just practice saying that for the exam. How about physiological dead space? This seems to be a bit more difficult, a bit more annoying to describe. What do you reckon?
Yeah, so the physiological dead space, again, it's measured using the Bohr equation, where it assumes that the carbon dioxide expired, the amount of carbon dioxide expired equals the total amount of carbon dioxide in the respiratory system. So it works on the principle of, goes back to our chemistry days where it's C1V1 equals C2V2. Again, really, maybe just have a look at this equation when you have time. But basically, your VT, which is your volume of your tidal volume, times the fraction expired CO2 equals VT minus VD, which is your tidal minus your dead space, times the fraction of alveolar concentration of your CO2. When you rearrange this, it becomes a bit more of a familiar equation of VD over VT equals, in the numerator, in brackets, P alveolar CO2 minus the expired CO2 over the alveolar concentration of the CO2. Is that right, Lahiru?
Yes. So actually, just say that again for everyone.
So VD over VT equals the P alveolar CO2 minus the expired CO2, all over the P alveolar concentration of CO2.
Yeah, that's exactly right. There's a few parts of this which make it a bit confusing. But so the first thing to know is don't worry too much about the derivation for our exam. VD over T equals P alveolar CO2 minus P mixed expired CO2. So it's P little e with a little dash above it. So the dash means mixed expired over the total of P alveolar CO2. This is called the Bohr equation. Now, P alveolar CO2 is actually hard to measure. Like you've got to get down to doing an end tidal concentrations. It can be a bit inaccurate depending on, it will be inaccurate because that's literally what you're trying to measure. So what they do is this thing called the Enhoff modification. So P alveolar CO2, we approximate that with P arterial CO2. So again, we're trying to figure out how do you get these values to actually figure out how much dead space there is. So you just take an arterial gas, your PaCO2, you substitute in for big A, P alveolar CO2. How do you reckon you get your mixed expired CO2?
The mixed expired CO2. How do you get the mixed expired
Yeah, it's a tricky one, right? So
Yeah.
it's not an end-tidal CO2 because that means that's the concentration not in, a mixed explosive is not including all of that dead space gas. Your end-tidal CO2 is higher than your mixed expired CO2. That's a really important point here that a lot of people might kind of forget or mistake here. So what you do is you essentially take all the expired gases, which includes your dead space gas, which has very low CO2, and then you measure that. So it's called a Douglas bag. It collects all the expired gases. You measure the PCO2 in that Douglas bag. That's your complete mixed expired gas CO2. The normal range is about 0.2 to 0.3 during normal resting breathing. And that's pretty much what you need to know with this. What do you reckon is Fowler's method? Does that have more or less than Bohr's method if it's calculating volumes?
If it's calculating volumes, does Bohr have more?
Bohr has more. Hey, that's good.
Yeah.
Bring it. Bohr has more because Bohr will calculate all of it, whereas Fowler's is much less. It's just the anatomical dead space.
Yeah. And I guess, yeah, similar to like when we talked about the Enhoff's method, I think when you do that, it's going to be slightly larger than the Bohr's physiological dead space when you calculate everything out. Just because the arterial CO2 is generally going to be a little bit more than the alveolar CO2, as if you think about it, the gas exchange is good, but it's never 100%.
Yeah, exactly. And in well lungs, you pretty much might as well say it's equal, but yeah, in disease states, potentially not. But guys, that's dead space. We went through a lot of the important points. Really get your definitions absolutely spot on. Like, just remember in the exam, the first question is often just definitions. If you're getting them incorrect or slowly giving answers of these definitions, that's a real problem. Like if you spend a good amount of time just being really sharp with your definitions, which it means I'm imagining what's going on. When I'm thinking dead space, I'm imagining the lungs, I'm imagining anatomical, I'm imagining alveolar, I'm imagining a pulmonary embolus there blocking the artery. And I'm imagining this so I can then talk about it in these terms. Again, it's really easy to confuse things like PE, which causes both dead space and shunt or VQ mismatch for other reasons, but from the purposes of the mechanics of something obstructing a vessel or capillary, it causes dead space. But actually, just to go on, hey, actually, you don't know why pulmonary embolisms cause like kind of shunt or anything like that, do you?
No, well, I was listening to your podcast the other day actually. Then I remember that, but I don't remember exactly.
No, it's not. So yeah. It causes shunt because a disease state like PE or pulmonary embolism, it has multiple effects. It's a foreign substance or maybe not a foreign substance in every situation, but it's not good for the lungs to have it. So it causes a level of inflammation. That inflammation can cause shunt and VQ mismatch in itself. So that's one of the things. Inflammation in your airways might cause diffusion abnormality, change your VQ ratios, cause all of this VQ mismatch, may even cause APO or fluid sequestration in your alveoli. So that could be a cause of shunt due to pulmonary embolism. But also if it's a big enough pulmonary embolism, suddenly you've got all of this blood that used to go through one lung being redirected and going through the other lungs. So suddenly you've got far less optimal VQ matching in the lung that is good, because now all of that cardiac output or a proportion of the one side of the cardiac output for the lung has to go through the other side. So a couple of reasons there why you might get a change in AA gradient or some level of shunt, VQ mismatch, diffusion abnormality from PE.
Yeah, and that shunt and the VQ mismatch is something that we're definitely going to concentrate on in the future.
Beautiful. Thanks very much, everyone, for listening and watching. Yeah, good luck with your study, good luck with the exams, and we'll see you again next time.
Thanks, everyone. Bye.
Now, what's new with ABCs of Anesthesia is that we're forming a whole bunch of very comprehensive courses for every stage of your anesthetic journey, from medical student to procedural skills, from foundations in anesthesia, as well as really important exam lectures and clinical anesthesia courses as well.